So, good morning, class. You are welcome to our lecture today. Sheung, can you mute yourself? Sheung, can you mute yourself? Okay, that's good. So let's go straight to what we have today. This is the second round of meeting for uh, this session. I believe you can see my screen. So just to quickly review what we discussed last week. In the last lecture, we introduced ourselves to probabilistic graphical uh, models, popularly called PGM. We talk about the two uh, combinations of PGM, basically uh, graph theory and probability theory. And we look at the historical development of the PGMs, the foundation, and then the role of the artificial intelligence. And uh, we talk about the Bayesian networks and the Markov networks, and we try to uh, look at the difference or differences between the two. Uh, of course, the two of them uh, form the uh, the types of graphical models that we have: the Bayesian network and the Markov networks. One is uh, directed graphs, or it uses directed graphical models. The other one uses the undirected graphical models. And we uh, show examples. I hope you can still recollect those examples that we use. And then we concluded that chapter with applications of the PGM. In particular, we look at linguistics and natural language processing, how PGMs are used to model sentence structure and word dependencies. We will still do more of that, but PGMs also have applications in health and medicine, education, transport and navigation, and diverse other fields. So that's the quick rundown of uh, the first lecture, which of course happened to be chapter 1 of the manual. Now we want to move straight to chapter 2. But if you have any uh, comments, any feedback, feel free to let me know. Um, so if you want us to continue, just say, to be sure you are following me, can you just type yes in the chat menu? I want to be sure you are following me. Type yes in the chat menu. I can see Oluwaseun. Oyeleye Dupe. That's good. So, uh, yeah. So let's continue. So our focus this morning will be on the fundamentals of probability theory. As you know that this course is anchored on two major fields: the graph theory, which I discussed earlier, the graph theory, and of course the probability theory. Our concern now will be on the probability theory. Um, and probability is a measure of uncertainty. So in life, uh, many things are not uh, certain. Uh, you are not sure whether it will rain tomorrow or it will not rain. You are not sure if, even if I'm not sure, let me use myself, uh, whether one will be alive uh, next year, even tomorrow, even next moment. Nobody is sure. If your wife is, uh, I mean, a newly wedded couple, for instance, they are not sure how long the marriage will last, except so nobody they can't say precisely this marriage will be for 20 years, 50 years, 100 years before death, you know. So there are so many things that we are not too sure of in life. So probability measures uncertainty. Uh, and uh, our focus will be to look at uh, some important concepts in probability. So concepts like even the probability itself, concepts like the rules. So probability have rules. Um, concept like the probability distribution, concept like the joint probability distribution, concept like the marginal probability distribution, and concept like the conditional probability distribution. Um, so these concepts are very, very essential uh, fundamentals in probability. And we are going to take it from the very basic perspective because of our linguistic colleagues. So you need to have a very firm grasp of what probability itself is, the rules, which they also often call the axioms, Then the distribution, the joint, which we call the joint PD, the marginal MPD, and then the conditional CPD. These are very, very uh, important, crucial concepts. Now, in the manual, of course, we talk about we define our probability to be a measure of certainty. And the simple measure is this, which we are familiar with, is simply uh, the number of favorable outcomes, number of favorable outcomes over number of possible outcomes. So this is the simple definition of probability. So, for instance, if you have in a class, you have boy, boy, girl, girl, boy, boy, girl. So, so this is the class, and we are now interested in selecting a student randomly from this class. And let's say we are interested in the probability of selecting a boy from this class. So we simply use this definition and say, indeed, what are how many students are boys? That represents the number of favorable outcomes. So we have this, we have this, we have this, we have this. So how many? That's the number. In this case, you have 4. Out of possible, over number of possible outcomes. Of course, that represents the number of students in the class. You have this. So all of them, which is 1, 2, 3, 4, 5, 6, 7. So this is 7. So the probability of selecting a boy from this class is 4/7. And of course, the probability of selecting a girl is 3/7. So this is the simple way that probability is measured. So it's simply the number of favorable outcomes over the number of possible outcomes. So if you have to, for instance, if you can perform an experiment, so you need to first of all list all the possible outcomes. So if you have a coin and you toss it, it's either head or tail. So there are 2 possible outcomes. And so if you are interested in head, that's the outcome of interest. So how many heads are possible in a single toss? That's one. So then you have 1/2. So this is the frequentist approach of determining the probability of an event. Feel free to ask questions as we continue. So that takes us to another concept which we call the random variable. So in the lecture note, we talk about random variable and probability distributions. So random variables uh, help us to uh, uh, convert our uh, possible outcomes. We are able to uh, define our uh, outcomes. So by definition, a random variable is anything that takes different values, depending on chance. Um, so, and you have example there. Uh, so by definition, I'm here. The random variable takes on different values depending on chance. So we have example. Uh, if we are tossing a coin, you know, uh, we don't know what will happen. So all possible outcomes uh, in this toss will be head or tail if you toss the coin once. So you could have head or tail. If a woman is pregnant, the possible outcomes could be male or female. You know, we are also talking of rainfall. It's either it rains or not. Um, there are also outcomes that are not binary. There are outcomes that could have more than two or three or four possible outcomes. For instance, in the university, a student could graduate with first class. That's a possible outcome. Could graduate with the second class upper, second class lower, third class. No, of course, we also fail. So we talk of possible outcomes. So let's come back to the one we are talking about here. So uh, in tossing a coin, the possible outcomes could be head or tail. So which means we could define a random variable to represent the possible outcomes. So we could say let x be the be the outcome. Uh, so in that case, we could have x to be head or tail. So to either be x or tail. And then we could say that experiment, for instance, we define it at experiment one, you have a head or a tail. So because this experiment is such that it can take two possible values, that's why it's a random variable. If you have another experiment of throwing a die, and then you could define that experiment too to have possible outcomes 1, 2, 3, 4, 5, 6. And because you will have 6 possible outcomes, then the variable x, well, let's say y this time around is a random variable that can take any of these possible values. So um, is 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 a random variable that take 1, 2, 3 up to 6. So random variables takes or take different values. The value, so is a random variable simply because it's not taking only one value. It could take 2 or more values. So, but when you have a random variable and we define the random variable, like in this case, let's go back to the coin. So in that experiment of tossing a coin once. So the possible outcomes could be head or tail. And then, so this is the X. The realization of the random variable is usually denoted with small x, so which means x could take, no, the realization is the small x. So when I write small x, it could be head being the realization or tail being the realization. So the probability of x equals to any realization. In this case, it will be probability of x being head. In this case, it will be probability of x being tail. I want you to start getting those notations properly. So x capital represent the random variables. So random variables are represented by capital letters. And the small letters represent the realization of that uh, experiment. So this table is what we call the probability distribution table. So we call it the probability distribution table, or simply say probability distribution. So probability distribution simply gives us all possible uh, 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 probabilities, the probabilities associated with all possible outcomes. The probability associated with all possible outcomes. So for the probability when the outcome is head, that is written here. The probability when the outcome is for tail is here. And then you have the total here. So in the probability distribution table, the total is always equals to 1. So the total probability is always equals to 1. So in this particular case of tossing a coin, we can now have the probability distribution table. So for head, for tail, this is X, this is total, and then we can now have probability of X. So what is the probability of head appearing? So if you go back to how we compute probability as the number of possible favorable outcomes over possible outcomes. So which means in our experiment, we have possible outcomes are head or tail. So if I now want probability of head, then the favorable is head, and it appears only 1. So which means I will have 1. The possible outcomes in this single toss is 2. So which means I have over 2. So that's how in this distribution table, probability distribution table, here will be half. Again, if I want probability of tail, that is probability of the random variable when the outcome is tail, that again will be half. So that's why the total will be equals to 1. So this is a probability distribution table. So in the probability distribution table, each possible outcome has the corresponding probability value. So which simply tells us the degree of uncertainty or certainty, the likelihood of head appearing is 50%. The likelihood of tail appearing is 50%. And the total probability is 1. So in a probability distribution table, you are able to see all the possible outcomes and the corresponding probability value for each outcome in the sample space. Right? That is the point I want to make here. Let's again I'm taking it in a very elementary way. I know uh, some of you may be more, but it's because of our linguistics colleague. Now, let's go back to the experiment 2, which is to throw a die. And in that experiment, so I call that E2. What are the possible outcomes? 1, 2, 3, 4, 5, 6. So if we throw the die, there are 6 possible outcomes. And so we can define a random variable y, for instance. So let y be the the outcome. So if y is the outcome, then whenever I write y equals to small y, then small y will be the realization at any point in time. So because capital Y can take could be so 1, so the realization will be 1. It could be 2, so the realization is 2. It could be 3, the realization is 3. So the realization again is in lowercase, in small case, but the random variable itself is in capital uh, letter. Remember that notation very well. So I can also, as usual, have the probability distribution table. Probability distribution table. So in that table, I'm going to have the random variable. In this case, we have used y for the notation. So the random variable y. So the random variable y could take 1, 2, 3, 4, 5, 6. And then, as usual, in the probability distribution table, you also have the total. On this row, you are going to have the probability of y taking a particular uh, realization. So here, I'm interested in the probability of y being equals to 1, which means the favorable outcome I want is 1. So the probability would then be that favorable outcome. How many occasions, how many times do I have in it here? And it's only once. Then that will be 1 out of possible outcomes. What are the possible outcomes here? 6. So this will be 1 all over 6. Again, the probability of that random variable taking the value 2. 2 appears only once here. So that will be 1. Possible outcomes, again, 6. And so on like that. So 1 over 6, 1 over 6, 1 over 6, 1 over 6. So this table again is called the table of probability distribution. The total again is equals to 1. Uh, I believe you are following. So if you are following me, type yes. If you type yes, if you are following me, and if you have any question, yes, I can see Adedabala, yes, Adetona, okay. I'm trying to save time, that's why I'm not engaged. But if you are following uh, and you have a question, feel free to ask your question. Now let's do something. Uh, so I believe maybe um, Kafayat will come in after this, and you might also be able to engage her, maybe with other examples. So let's move on. You remember I mentioned, I listed those concepts that you need to get familiar with. One, the probability, which we've talked about, which is simply measured in terms of number of favorable outcomes divided by the number of possible outcomes. Now we talk about the rules of the probability. Uh, so one thing you must have noticed, so in our manual, we talk about uh, these rules. They are more than that, but this is basic. So one, you will notice in all in the probability distribution table that we have constructed, one, the probability is always between 0 and 1. Probability is always between 0 and 1. So when we talk about that, in uh, if you have a number line, so you could have 0 here, you have 1 here. So any value below 0 is negative. Sorry. Any value below 0 is negative. Any value above 1 is, of course, any value above 0 is positive. So 0 is so any value from here, no, is positive. Any value here is negative. So, but even on the positive side, probability can only take value that is between 0 and 1. So we can say that probability is non-negative. Non-negative. Sorry. So we can say probability is non-negative. What that means is simply that probability does not take a negative value. So you can't have minus 0 point something as a probability. So it can never be less than 0. The other thing now is that it must be positive, yes, but it can never be greater than 1. So probability lies between 0 and 1. It's non-negative means it's never in this region. It's never in this region. So it's positive means it's greater than a 0, and of course cannot also be greater than 1. So it's between 0 and 1. That is very important for uh, uh, that rule is very, very important. Now, this second rule is that the total probability of all outcomes must be equals to 1. And that's what we've tried to demonstrate in the distribution, probability distribution table that we have created. So what that rule is saying is that the total probability of all outcomes. So in this case, all outcomes are being tabulated head, tail, and the individual probability also uh, have been given. So it's saying the total probability must always be equals to 1. So this table is a true, it represents a true probability table. So if you are to look at any table to know whether it's a probability table, that table must have all the possible outcomes and their associated probability values. That's number one. The probability values must be non-negative, and they must also not be greater than 1. That is another second thing. The third thing is that the sum of all the probability values must be equals to 1. If that is captured in the table, then that table is a probability distribution table. Great. We also uh, demonstrated that here. So this is a probability distribution table. Why? Because you have all the possible outcomes listed, and for each of them, you have their probability values. And then the probability values, each probability value is 1, non-negative, 2, not greater than 1. And then 3, the sum of all the probability values is equals to 1. So again, this is a probability distribution table. So if this is clear, which I believe, so that means we have discussed the probability. We have also understood the rules. And again, we can all be able to construct a probability distribution table for any statistical experiment. Anybody in this class now, you should be able to construct a probability distribution table and say that this table is truly a probability distribution table. If you are able to do that, type yes. If you know you can do that, type yes. Yeah, I can see Adetona can do that, Adedamola can do that, Oyeleye can do that. So, for instance, if I give you a simple experiment like experiment of tossing a coin twice. Let's say you are tossing a coin twice. So that experiment 3, which is tossing a coin twice. And you are asked to construct the probability distribution table for this experiment. So what you want is a table that will be able to show all possible outcomes, to show the probability associated with all possible outcomes, 3, show that the total probability is equal to 1. So, first of all, we might, as usual, talk about experiment 1 and look at all possible outcomes. So, let's say in the first toss, you will have a head or a tail. So these are possible outcomes, and this is the first. If you are throwing it twice, this is what you get in the first. Then the second time, if you throw it, you will have a head or tail. If the first was head, if the first was tail, then the second time you will have head or tail again. So this is the second possibilities. And then you can now have the outcomes, which could be head, head, which means you have head in the first, head in the second. You could also have head, tail, which means you had head in the first, tail in the second. And you have tail, head, which means tail in the first, head in the second. And then you have tail, tail. So, which means we will have 4 possible outcomes. So our P3, we have head, 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 tail, tail, head, tail, tail. So this is the possible outcomes. So if we say, okay, we want to define a random variable x. So we define a random variable x. A random variable x will take any of these values: head, 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 tail, tail, head, tail, tail. So a random variable x will take any of those values. But we could also define it and say, uh, so, so to mean with, of we could also define it to mean to be the number of heads appearing. So which means we could say the random variable x represent the number of heads. So in this case, if we define it as the number of number of heads, then the number that number of heads for head will be 2, for head tail will be 1, for tail head will be 1, and for tail tail will be 0, which means that random variable x will either be 0 in the other way around, or 1 or 2. That's the random variable. So we are now converting it to number. So which x is simply number of heads. So we could have number of heads to be 0. And when it is 0, it means no, on the 2 occasions of tossing, you have tail tail. When it is 1, it means on the 2 occasions you either have head tail or tail head. And when it is 2, it means on the 2 occasions of tossing the coin you have head appearing. So we can now construct a probability distribution table. So our probability distribution table would then have the random variable and then the possible values could be 0, could be 1, will also be 2. And then we will have the total here. And then we can now say probability of the random variable taking a particular realization. So here I'm interested in the probability of the random variable being 0. In which case, I'm interested in what will be the probability that no head appears. What will be the probability that no head appears? So I will come here. What is the favorable outcome? This is the only occasion when head does not appear, and it's only once. So I have 1. Out of how many possible outcomes? 4. So I have 1/4. So here I'm talking of probability of x I'm talking of probability of random variable x taking the value 1, which means I'm interested in when the random variable is 1. That is, when the number of heads is 1. And that can only happen here and here. So I have only 2 favorable outcomes. So which means I have 2 out of how many possible outcomes? 4. So which means I have 2/4. And finally, I want the probability of x taking the value 2. That is, on the 2 occasions head appear. So that is only going to happen in this case. So I have only 1 favorable outcomes. So 1 favorable outcome out of 4 possible outcomes. Now, you will agree with me. If you now add this up, this is 4/4, which is equals to 1. So this is a probability distribution table because we see all possible outcomes, we see their corresponding probabilities, and we see that they sum up to 1. So I've given you another example. So you must always be able to develop, construct your probability distribution table and be sure that you know all the possible outcomes and you can compute the uh, associated probabilities. Right. So the next concept we want to talk about is the joint probability. So that's the next one I want to talk about before I now hand you over if we to Kafayat. Kafayat will possibly review what we have done with you and possibly, if time permits, extend. And then later, Connie will ask few questions to test your understanding of the lecture, from the manual, and then those questions relevant to the concept that we have talked about, and then give you whatever exercise or assignment you need to do. So let's talk about joint probability distribution, JPD, joint probability distribution. Because this course is anchored, on probability. That's why you need to be able to understand probability, the concepts, very well. And that's why we are taking it in very elementary form like this. So JPD, joint probability distribution. In the note, in the manual, no, in the manual, there are actually three concepts that you need to understand: joint, marginal, conditional. Joint, manual, conditional. So, so we will focus for now on joint. And the when we talk of the word joint, so it means you are talking of two, minimum of two, minimum of two events happening together. Two events happening together. So if we go back to, you could have more than two events, but for my for the for demonstration, now we are going to focus on just two events. Earlier, we've looked at these two events separately. One, the event of tossing a coin. Two, we've looked at the event of throwing a die. So we treated them separately. But we could also have an experiment in which the two of them are done simultaneously, which means in that experiment, so I will call it experiment maybe 4. This time you are tossing, or, or, or if you like, you are throwing a die. A coin and a die. You are doing the two of them simultaneously. So what will happen is that in the coin, you will have head or tail. So if you had a head in the coin, then in the die, 6 things can happen. You could have a 1, so for the die, 1, 2, 3, 4, 5, 6. Hello. Hello. Are you able to hear me? Sorry.
Yes, yes, we can hear you now, sir.
Okay, sorry. We, the call interrupted the lecture. So let's continue.
Yes, sir. Hello, sir.
So I was saying that in the
Yes, we
coin
can
we
hear you
could
now,
have
sir.
a head. Yeah, thank you. In the coin we could have a head, and then in the die we have a one. No, so the same thing can happen here. We have tail in the first in the coin and one in the die. So we have 1, 2, 3, 4, 5, 6. So which means uh, we could have all possible outcomes. So we could have possible outcomes. Uh, so we can we can use random variable x for the coin. So for the coin, which could be head or tail, we could use y for the die, which could be 1, 2, 3, 4, 5, 6. And then because we have two random variables now, we can now define a joint probability, a joint distribution. So if it's going to be joint, then we will be having x, y. We will be having x, y. So which means in this case, I will have head 1. I will have head 2. I will have head 3. I will have head 4. So you can see I'm having joint because we have we are we have two events together. So H5, H6. Same way, tail 1, tail 2, tail 3, tail 4. So which means I could possibly have my joint distribution to be H1, H2, H3, H4, H5, H6, T1, T2, T3, T4, T5, T6. So this is called joint distribution. This is called the joint distribution, which is simply say all the possible outcomes in the experiment of tossing a coin and throwing a die. These are all the possible outcomes. So when have two or more events together, then you are talking of the joint. You are talking of the joint distribution. Get that very well. So I could also have experiment of tossing a coin, throwing a die, and also checking whether it rains or not. So I could have X, Y, Z. X will be for coin, Y will be for die, and then rain will be Z. So you could have two or more, events, two or more events in your experiment. So, as usual, we can also construct a joint. So we can talk about joint distribution table. Sorry, uh, joint probability distribution, which is even what we want to talk about. So, and it's the same principle in the joint probability distribution. We are going to look at each of these joint outcomes and their probabilities. So we look at each of them. So in which case, we will have a table that will show X, Y, that is, it will show H1, it will show, of course, we can put, so H2, H3, H4, H5, H6, T1, T2, T3, T4, T5, T6, and then total. And then here it will be probability of X equals to realization, probability of Y equals to realization. So we will have something like this. So anytime I want probability of the coin showing head and the die showing one, then I want this probability. So I will write it as probability of the die showing head, the coin represented by random variable 1, the die showing 1. That's it. The next will be probability of the coin showing head and the die showing 2. Up to the last one here, no, like that. And so the probability of the coin showing tail and the die showing 6. So each of these is called joint probability. Joint probability. So it's probability of head in the coin and 1 in the die. So we are using probability of X and Y, probability of X and Y. So hand, remember, we are still coming to all of that. Probability of head, no, and 1, probability of head and 2, probability of head, tail and 6. So we now, so for this probability, this is appearing only once, which is the number of favorable out of how many possible outcomes. In this case, how many? 12. So this is 1 over 12. No, the same thing, 1 over 12, 1 over 12. Number of favorable outcomes over possible outcomes, 1 over 12, 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 and the total will be 12 over 12. So we have a joint probability distribution. And the interesting thing again is that for each joint probability, the probability lies between 0 and 1. It's not negative and it's not greater than 1. So you see how probability, how the joint probability distribution is constructed. The other thing again is that the total probability, even in the joint probability distribution, sum up to 1. So this is equals to 1. So that is joint probability distribution. You should understand, you should be able to construct the joint. And in most practical problems, you are going to have 2 or more events. You are going to have 2 or more events, as is demonstrated here. The event could be it rains, so we use A as random variable, or event A to stand for it rains, and B to stand for the grass is wet. So this is like saying you possibly have, so if you are talking about rain, so you could have rain, then no rain. So this is pause. So let me use, instead of saying no rain, let me say you have, for A, it could be rain, then it could be dry. So, which means no rain. Okay, no, let me go back because of something I've seen now. So you could say rain, no rain, so no rain. Then that's the situation. These are 2 possible situations when it comes to the rain. So if it rains, then the grass could be wet, so not wet. Of course, if it rains, the grass will be wet. That's the Or if there is no rain, then you could have wet, also not wet. So again, we may be interested in the joint probability that it rains and the grass is wet. So it means it rains and the grass is wet. We are interested in this. This is our favorable outcome. But you need to know all the possible outcomes. So A represent it rains, B represent the grass is wet. So in most practical situations, we will be looking at joint probability. In other words, two events, occurring the same time. So this where I will stop. If you have any quick question before I hand you over to my colleagues. Yes. No question, no comment. Are you saying you don't? Are you saying you don't understand anything in the class, in the lecture? Hello, the class is too quiet.
No question, sir. Your class is well explanatory.
Thank you. So, yeah. Kafayat, are you there?
Yes, sir.
So,
Yes, sir.
you have the floor. And as I've said, after Connie will come in with questions to evaluate how the class has been following. And then, of course, we think of uh, quiz or question exercise for the class. Thank you very much.
Thank you very much, sir. Good morning, class. Good morning, everyone. All right, so Prof has explained to us so much about the lecture for today. And he also gave us a review of what we did the last class. Like Prof discussed in the last class, the concept of Bayesian network covers two things, two basic concepts. That's the graphical theory and the probability theory. So today he has introduced to us the probability theory, and we stopped at the joint probability distribution. So I'll just give us a few more examples to widen our explanation on this concept. So to start with, probability theory itself. As Prof said earlier, in probability theory, there are few things to note. The first thing is the random experiment. In any probability, there must be, for probability to occur, there must be an experiment. That is, something must happen. We can now look at what is the probability of this thing happen or it will not. That's what we call an experiment. And then the other thing is the sample space. What do we mean by sample space? That's the all set of possible outcomes from the experiment. And lastly, the event itself. By events, we mean set of favorable outcomes from the sample space generated from the experiment. And also, Prof discussed the rules of probability that we have. The first one is that probability values must not be negative. That is, we can't have less than 0. Then that's where the negativity comes in. And also, probability must be between zeros and 1. That is, must not be greater than 1 and must not be less than 0. And the third part is that all sum of all probability values must be 1. Yeah, so let's look at just a few examples in addition to the one that Prof discussed with us. Prof has explained to us generating a sample space from tossing a coin experiment. If we are to toss a coin, we either get a head or a tail. But what if we look at flipping or rolling a dice or a 2 dice at once? So let me try to see if I can project my notes. Sorry, I'm trying to bring up my whiteboard first. It's taking some time so that I can get a better explanation of the example.
Are you press the share screen, the button for the share screen? Are you able to do that?
For share screen, yes, sir.
Yeah, press the button for screen sharing, and then in the window, go to entire screen.
Okay, sir, I've done that, sir.
Then click the image that you have there, and then the share button will highlight.
Yes, I've done that, sir. So I'm trying to. I've not used whiteboard on my Meet before. That's why it's taking some time for me to. Okay, so can we all see my screen now? Please confirm that you can see my screen.
Yes.
All right, thank you very much. So to start with the example of tossing, let's say, for example, we want to roll 2 dice at once. And then let's examine the probability of getting a sum of 8 at once. First, we look at how many possible outcomes can we have from rolling 2 dice at once. To get this, we look at the number of possible outcomes on the first die, and then the number of possible outcomes on the second die. I'll use the approach to solve this. There are many approaches to solve this, but to make it simple, simpler for us, to start with, let's say here we have the number of possible outcomes on the first die. And then we also have, on this line, we have the number of possible outcomes on the second die. So on the first die, let's say rolling the first die, I have 1, and on the second die, or let's start with, on a die we have 6 sides, right? On the first die, I either have 1 to 6, and on the second one as well, I either have 1 to 6. So let's say on the first one, we have 1, 2, 3, 4, 5, and then 6. And also on the second one, we also have 1, 2, 3, up to 6. Now rolling the first one, we can either have 1, 1, right? And on the second one, we can either have 1, 2. Third one, we have 1, 3. Please, if you have any question or if you don't understand what I'm doing, you can just unmute and ask so that before I go far, you can clarify this. Now, up to, we can also have 1, 6. Remember, we are looking at the probability of getting a sum of 8. To save time and due to the board we are using, let's move to the last line. Here we have 6, 1. Six, 2, 6, 3, 6, 4, up to 6, 6, right? So let's go to the line 5. Here we can have 5, 1, 5, 2, 5, 3, 5, 4, up to 5, 6, right? Now let's go to line 4. Let's assume there's line 4 here. So, please pardon the space and the tidiness in the whiteboard. So let's say we have 4, 1, 4, 2, 4, 3, 4, 4, then up to 4, 6. And let's say we have 3, 1, 3, 2, 3, 5, up to 3, 6. Then we can also have 2, 1, up to 2, 6, right? So our interest in is in finding the probability that we have a sum of 8. Looking at this table, how many sum of 8 can we get from all these values? Looking at it, we can say, let me start from line 1. 1 and 1 can give us 8, right? Up to 1 and 6. That's the highest, which is 7. Now, moving to the next line, we have 2 and 5, 2 and 6. Now, please kindly follow me with your notes of board. So we have 2 and 6 in the next line. That gives us a sum of 8, right? That's one of the favorable outcomes. Now, to the next line, that is the line 3. We also have 3, 1, 3, 2, 3, 3, 3, 4, 3, 5. 3, 5 also gives us a sum of 8, right? 3, 6 is already 9. Now to line 4, we have 4, 1, 4, 2, 4, 3, 4, 4. 4, 4 gives us a sum of 8. Anything else on that line give us above 8. Now moving to 5, we have 5, 1, 5, 2, 5, 3. 5, 3 gives us sum of 8, right? Moving to line 6, we have 6, 1, 6, 2. Yes, 6, 2 gives us a sum of 8. 6, 3, 6, 4, and the likes gives us above 8. Now, our interest is in finding the probability that we have of getting a sum of 8. Now, as Prof discussed earlier, what's the formula for probability? It's very simple. The probability is just the ratio of the number of favorable outcomes over total number of sample space. In this case, this is our sample space, right? Now, what is our favorable outcomes? Those are the values that gives us the sum of 8. That's the 2, 6, 3, 5, 4, 4, 4, 3, and 6, 2. And those are 5 in total. Now, that's our favorable outcome. How many favorable outcomes do we have in this case? We have 5. And then the total number of sample space. In this table now, who can tell me how many sample space? How many sample space do we have in this table altogether? Timothy, do you have an idea?
36.
36. Thank you. That's very brilliant. So we have 36. If we count this table one after the other, and the shortest form to get it is we have 6 on one side and then 6 on the other side. That's 6 by 6 gives us 36. Now we have 5 over 36. That's the favorable outcome over total number of sample space. Now the probability of getting a sum of 8 from rolling 2 dials at once gives us 5 over 36. So I want to believe we understand. Please, do you have any question before we move to the next example? And I'll be glad if you can solve this explicitly in your notes before the next class so that you can understand better what you have done. Is there any question before I move on? Okay, in the absence of no question, let's move to the next example. Prof also discussed was about joint probability distribution, and that's the probability distributions of 2 or more probabilities of more events occurring at once or more than once. Yeah, so we just hello, can you hear me? Hello?
Yes, you can. Yes, I can
Okay,
hear
I
you.
was asking if there's any question. Did anybody say something? I lost my network for some time. Okay. Okay, so the second example, let's say we roll two dice at once or at the same time, and we want to find the probability that number 3 will occur twice on that dice. Like when we roll two dice at once, number 3 will occur twice on a dice. So first, we look at the number of possible outcomes. Number of possible outcomes for rolling a die is 1 to 6, right? And either have 1, 2, 3, 4, 5, and 6. That's the number of possible outcomes for rolling a first die. Let's say the event of rolling a first die, let's call that A. A, right? Let's call the event of rolling another die, like Prof explained the other time that we use random variables to denote events. Okay. So in this case, I'm using the random variable A to denote that the possible outcomes of rolling the first die is A. Now the second one, let me use B, which is also 1, 2, 3, up to 6. So both dials have 6 possible outcomes, right? Now, what's the probability that 3 is occurring on each of these dials? First, the probability that 3 is occurring on the first dial, that's A. In this case, probability of A is what? The probability that 3 is occurring in the first dial, A, is what? In this case, anybody?
1/6.
Thank you very much, Louis. 1/3. Very good. 1/3. And also the probability that 3 is occurring on the second dial, that's the probability of B. In this case, which is also 1/3, right? Now, we are interested in the probability of that 3 is occurring on both dials. That's probability of A and B, which is the joint probability. Let's look at probability of A and B. And that is probability of A multiplied by probability of. Yes, Dupe, you want to ask a question?
Yes,
Of B.
sorry. You said the probability of 3 occurring in a die. I think I don't know. I don't. You said it's 1/3. I thought the
Yes.
total all outcome should be over 6. Or am I done? I don't
Yeah.
understand. Sorry.
Thank you very much for that observation. Thank you very much. That should be 1
Oh,
over 6, since we are having 6 possible outcomes from the first dial and then 6 possible outcomes from the second dial. Thank you very much, Dupe, for that observation. Now, the joint probability will be probability of A and B. That's the probability of A multiplied by probability of B. Although that's when the events are occurring independently. We get to understand this better in the next class. So probability of A multiplied by probability of B will give us what? That will be 1/6 times 1/6. And that will be 1/36. And that's the joint probability distribution. When we roll 2 dice and 3 occur twice on the dice. So I will take questions before Ms. Tony come on to take the quiz with us. If you have any questions, please ask. Okay, so in the absence of none, please, Miss Oni, you have the floor.
But your hand is up. Okay.
Sorry, that's a mistake. Thank you.
All right.
Okay,
Miss
good
Tony,
morning, everyone. So we have 10 minutes to quickly do the multiple choice questions. But I think the class has been okay. Mr. Adedamola, your hand is up.
Good morning, everyone.
Yeah, good morning.
I just felt I should say this to the house. I don't know, nobody said me, but I just felt I should say it. There's this prof book. I think something on descriptive. I don't know. I'll get the name. So I'll advise many of us to like get it because the concept of probability is kind of well dealt with in that book. Because in this course, just like I've observed, we're going to be very grounded in probability, especially the fundamentals of it. So I will just want to, I have to advise that we just lay our hands on that book so that we can, get the concepts better, so we can better prepared. Thank you.
Thank you very much. That's a brilliant advice. Okay, so for the multiple choice questions for today, we are all going to be doing this together. I'm not just going to read the questions and you just type in the answer. We are going to rotate each of the questions. We are about 8 students here. So you just read your question. If you want to pick number one, just pick number one. Okay, I'll call your name, then you pick the next question, read it and explain. We know what the answer is because we have the answers already. So just explain maybe in one sentence the answer you think is correct and why. Do we get the approach we are using today? You have the manual with you, but if you do not have the manual, then when I call you to answer a particular question, just let me know that you do not have the manual. But please, I will advise us to get the manual so that this can be faster next time. Okay. So for question 1, okay, let me start with Adedamola.
Thank you.
Yes.
It says, what is a random variable? As just like Prof explained to us, that's a variable that can take different outcomes based on chance. It is called random because you cannot predict it. Predict it. So it is that is called a random, and oftentimes it is represented with capital, that's uppercase letters, and the variation is small case. So it's random. It's just a function that takes on numerical values based on chance. That's just it.
Yeah, thank you. I remember Prof also mentioning that if it is just one outcome, then it's not a random variable anymore because we already know what the outcome will be. So it's 2 or more outcomes. A variable with 2 or more outcomes. Okay, then the next person on my screen is Adelusi Toyin. Please pick question number 2 and read. Then explain to us what you understand by the answer. Question 2.
I'm yet to get the handout actually.
Okay, but please do that in time. Okay, Adetono, Adedoyin. Adetono, Adedoyin. Are you in the
I
class?
don't have the manual also.
You do not have the manual as well.
Yes.
Okay. Oluwaseun Gabriel, question 2. You want to leave me to do the reading by myself? Oluwaseun Gabriel. Gabriel, are you in class? Okay.
Good morning, ma.
Good morning. Yeah. Do you have the manual with you?
Yes, ma.
Okay, please read question 2 and explain to us the answer.
Which rule ensures all probabilities in a distribution add up correctly? Rule. Arrow.
Which rule did you call it?
It's just trying to call out.
I can't hear you well. Like your audio is. Your audio is. Should I say failing? Can you please repeat your answer and your explanation? Okay. Thank you. Thank you so much. Next person. Please, can you read question two? Can you please read question two for us?
So question 2 is which rules ensures all probabilities in a distribution add up correctly?
Yeah.
I think is normalization rules. Right. I don't know. Because I know normalization is you normalizing numbers between 0 and 1.
Yeah, normalization rule says part of the formula, or one of the formula is that summation P of X, that's probability of X,
Yes.
equals 1. And that's when we are
Yes.
dealing with discrete random variables. But if we are dealing with continuous, it's going to be integral of f of x dx equals 1. You're right. Then Timothy Oyeleye, please, question 3. I can't be answered too. Question 3.
Good morning, everyone.
Good morning, sir.
Yes, ma'am. What does joint probability measure? So, the question the answer is probability of two or more events occurring together. That means that they can occur at the same time. You can have more than two probability, according to what the prophet said in the morning to us in the lecture. That is C.
Events happening at once.
Yes.
Yeah, like more like a probability of the weather being sunny.
Yes.
You're using an umbrella. So
umbrella, yes.
Okay, thank you. Then I can see that Gabriel is back. Gabriel, can you read question 5 for us? Oh no, question 4. That is question 4. Yes.
Oh, okay, ma. Sorry, yes, ma. Marginal probability is computed by A, dividing through probabilities, B, multiplying joint probabilities, C, summing over joint probabilities, and D, ignoring prior information.
Okay.
Yes, ma'am.
So your answer and explanation.
Okay, I think my answer will be summing over joint probabilities.
Is okay.
Because marginal probability is more like saying probability of an event, of a single event occurring. So that's why I say it's more of summing over joint probability. So if you are considering two events, so for us to get the marginal probability of those two events, you have to sum each one of them together, so because they did not depend on each other.
Okay.
Yes.
All right. So you are very correct. Marginal probability is the probability of a single event or random variable, regardless of the outcome of the other. So when you sum over it, what you're calculating, when you sum over the probability, what you are looking for is the marginal probability of that single event. Okay, let's go back to the beginning. I know you already know who I'm going to call. Okay, I did that one. Question 5. Okay, we just have 10 questions. Question 5.
Sorry. Okay. It says conditional probability answers the question. Is what's the likelihood of both events happening? No. B, probability of an event given another has occurred. So that was it. And the answer is B. It says It gives us the probability of an event given another as occurred. So that's what conditional probability means. Like when we have like a typical example is from what we have in the manual. Let's go back to that again.
Yeah.
Okay,
Where
it said two have go of time.
Go ahead.
Okay. Should I read? The one that said
Yes,
two
go ahead,
variables
go
are
ahead.
conditionally independent if they are independent, giving us so okay, we have let A the cloudy one, B it rains, then the grass is wet. You know, the grass is wet, given that it has rained.
That's
Now
rained
in that case,
already.
we have a bit of C giving B. Hello?
Yeah.
Am I communicating?
Yes, you
Like we
are.
are taking B. Now we have B that it rains, C the grass that is wet. So the conditional probability of C that will now be that B has occurred. So that is a typical example of conditional probability.
All right, thank you very much. Adelusi Toyin, question 6. Oh, were you part of those that told me just now that you didn't have the manual with?
Yes.
Okay, and I guess I did turn on doing it too. Then let's go to Luashon Gabriel. Gabriel, please help us with question 6.
Okay, ma. Question 6. Two events A and B are independent if B, the probability of A and B occurring is probability of A plus probability of B for option A, and option B probability of A given B is equal to probability of B given A. Option C, probability of A and B occurrence equal to probability of A multiplied by probability of B. Then option D, probability of A equals to probability of B. So for me, I think the answer is C. Probability of A and B are independent if the answer is probability of A multiplied by probability of B. Just like the example that they give us during the class, when we consider a dice, unless a probability of, if you are picking a probability of having 5 in a set of a die is 1/6.
Okay.
That the outcome will be 5, and the probability that the outcome will be 8 in the set of a die, and you know, in a dice they are independent of each other, is that one too is 1/6. So if you want to find the probability of us getting 5 and 6, you have to multiply the answer, that's be 1/6 times 1/6. So which follows the pattern of C.
Okay. Thank you very much. So since they are independent, it means that their joint distribution is going to be 0. So adding 0 to that formula makes that formula to just be probability of A times probability of B alone, since 0 is nothing. So we don't have to add the joint probability because there is no relationship. They are not explaining one another. All right, so question 7. I think you have the manner with you.
Yes, I do. So for question 7, it says, what does conditional independence allow us to do in PGMS? I would say it's eliminating relevant variables because it focuses on the one that are really contributing to the outcome. So it doesn't focus on irrelevant things around it.
Yeah. Okay. Yes, thank you. We are going to be doing a lot of that in probabilistic graphical model as a course. We are going to be doing a lot of that. So we really need to understand all of these basic concepts. And just like what Mr. Adedamola Afolabi advised, please, if you can, apart from the course manual, please try to get the descriptive that he advised as well. All right, Oyelaya Timothy, help us with question 8. Oyelaya Timothy, help us with question 8.
Hello, ma. All right, my question here says, Bayes' theorem helps us to compute A, marginal probabilities, B, updated probabilities after seeing new data, C, frequencies of random events, D, the size of the sample space. So the answer is B. It helps us to update probability after seeing the new data. That is help us to see it help us to see the test, how the prior or how our belief in prior is. So the probability is updating the probability after seeing the new data of the belief.
Okay, thank you very much. I like the fact that you brought in the prior terminology into it. You know, when we talk about Bayes' theorem, one of the first things that should come to our mind is that, oh, now we are at that stage of where we have to deal with prior and posterior probability. So yes, I have totally agree with you that B is the correct answer, which says that Bayes' theorem helps us to update probabilities after seeing a new data. So it helps us to update our prior belief, and then we now have a posterior probability, a new probability based on what we knew before. Okay, so we need 2 people for question 9 and 10. I don't know. Okay, maybe Mr. Adedamola Afolabi should help us with question 9. Then a female, Oyeleye Dupe will help us with question 10.
Okay. Question 9. In the formula, probability of A given B is equal to B given A multiplied by probability of A given probability of B. So which term present prior belief? Please permit me to write this thing. We have probability of A given B equal to probability of B given A multiplied by, multiplied by probability of A over probability of B. Okay, yes. The prior here is probability of A. Probability of A is the prior. While we have the probability of B given A is the data. Is the data we have. You know, for me now, the probability of A given B is the posterior distribution. I mean, probability.
Yes.
Yeah, exactly. So I will know that probability of B must be greater than 0. So it's that just the the base formula. The probability is B is the total probability that we have.
Yes, that's the base formula. So the posterior probability equals the likelihood. That's the prior times the likelihood.
Like the data. Exactly.
Yes, divided by the marginal probability of B. So
B, yes.
you're correct. So the probability of A is a prior probability. All right. Exactly. Then the last one. Who did I assign it to? Oh, you let it do prayer.
So the last question says, which of the following best describes a real-world use of conditional probability? Option A, estimating exact weather on a specific date. Predicting exam score, knowing study time. Listing all possible outcomes. And the last option, calculating the area under a curve. The answer will be B. Predicting exam score, knowing study time. As we know, that conditional probability is the probability of an event occurring after predicting that one event has occurred.
Oh, yeah.
So now we can predict an exam score after knowing the study time a student puts into the exam.
Yeah. Yes. Okay. That was very brilliant. I'm happy that we kind of get the grasp of today's lecture. And please, for those of us that do not have the manual, please let's do well to get it, either the soft copy or the hard copy. We know where to get it from. So, thank you very much, Mrs. Kafaya. Mrs. Kafaya, are you still there? Okay, if she's no longer with us, let's just wrap it up for today. Thank you very much. I think an assignment will be dropped on our Google Classroom. Maybe just something to lay our hands on before the next class. The idea is for us to be able to read even before the class. So please, we know that we might not be able to get the entire concept. That's why there is a reason for the class. But please, let's try to read the materials, answer the questions that we assigned to us, and before the deadline. Yes, please, let's do that. So if there is nothing else, or do we have anything? There is nothing else. I would like to call it a day. So see you next class. That should be next week Friday.
Thank you.
Yeah, thank you.
Thank you very much.
Thank you,
you,
ma.
ma.